So, a very good morning to all, and welcome to my class. Today, we are going to start our new chapter, that is the topic structure, right? So, till so far, we are covered mole concept and equivalent concept in previous two classes, where we already covered all the important topics and the PYQ related to this chapter only, right? Now, from today onwards, we are going to start the atomic structure. So today and day after tomorrow, within two or 3 days, we are trying to cover this with the PYQ question as well, right? So this chapter is going to be very important, and this one is an important chapter in a point of view advanced paper, right? Many of the questions, basically one or two questions were asked from these chapters in every year advanced exam. So let's see which type of question they are generally asked, which topic they generally preferred. So we are going to cover all the important topics related to this chapter. I hope my voice is audible to you and my screen is also visible to you, right? Okay. So let's start with the today session. Start with the today topic that what we are going to study today. So first topic that we are going to study today is Bohr model, right? So the first one is Bohr model. So what is this Bohr model, beta? Right? So the before starting with Bohr model, we must know what are the postulates of Bohr. Then we are going to study their derivation parts as well, right? So what are the major postulates of Bohr model? Okay. So the major postulate, before Bohr model, various model comes into the picture, like J.J. Thomson model, Rutherford model of atom, where the J.J. Thomson model does not talk about the nucleus, where the Rutherford talks about the nucleus and they discover nucleus, and it states that the nucleus present inside the atom and the electron are revolving around the nucleus. But Rutherford is unable to explain the stability of the atom, how when the energy particle is revolving, how they are stable, because we know that whenever the energy particle is revolving around another particle, they continuously loses its energy, and its last is comes to become zero. So how's the atom exist actually? So these are the limitation of Rutherford model of atom. So the Bohr model comes into the picture, right? So what the Bohr model state, beta? The major postulate of the Bohr model are like first one, the revolution of electron around the nucleus occur in the circular path of the fixed radius and energy. It means जैसा कि रदरफोर्ड ने बोला था कि इलेक्ट्रॉन्स कहीं भी घूम रहे हैं चारों बगल. दिस इज नॉट ट्रू. इलेक्ट्रॉन्स आर रिवॉल्व ओनली इन देयर फिक्स्ड, राइट? सो द रिवोल्यूशन ऑफ इलेक्ट्रॉन्स अराउंड द न्यूक्लियस occur in the circular path of a fixed radius and energy. For example, some electron are moving in the second ray cell. It means they are moving in the second cell only because they have energy corresponding to the second cell only. For example, if the some electron moving in the third radius, it energy corresponding to the third cell only. So if they want to jump from one to another, so they want energy. Or if they want to jump from the higher energy state to the lower energy state, they emit energy. So these type of things are happen. It means these paths are called orbit, or we say stationary states, or we say shell, or we say stationary energy orbit. So there are lots of name of this. Basically, just remember these paths are called orbit, or we say cell, right? So this point you must remember. Now, and arranged concentrically around the nucleus. These are designated either as K shell, L shell, M shell, N shell, etc. Or many times you can write as 1, 2, 3, and so on. This integer 1, 2, 3 were designated as an N, or we say principal quantum number, which is given by the Bohr. Now, only those orbits, this point is very, very important. Only those orbits are valid in which the angular momentum is quantized, or we say have the value as an integral multiple of h upon 2 pi, right? So only those orbital are valid in which the angular momentum is quantized, or we have say that they have the value as an integral multiple of h upon 2 pi. It means nh upon 2 pi, where n is 1, 2, 3, 4, and so on, right? So this is the angular momentum, that is MVR, BVR, MVR, and this MVR is must be equal to nh upon 2 pi. So as we can see that the circular electron orbit, or we say stationary level in an atom. So this represent our nucleus. This is the first shell or K shell. This is the second shell, third cell, and the fourth cell. This cell, like first, second, and third, these are electron not allowed between the orbits, right? So as you can see that electrons are present only on the circular orbit, right? It means between this point, this point, this point, right? So electrons are not allowed between the orbits. Remember this thing, electrons permitted in the circular orbits only, like here electrons are present, here electrons are present, here electrons are present, and here electrons are present, right? And this represents the nucleus and this is the orbit. So this is the actual the diagram of the Bohr model of atom, right? Now this point is very very important. The energy of an electron within an orbit does not change with the time, right? The energy of an electron within the orbit does not change with the time. During the course of revolution, the electron neither lose energy or nor gains energy. Right? It means when the electron move in orbit, this is the limitation of Rutherford actually. Rutherford does not tell this point, right? Whether the energy, how energy decreases and how energy increases. So in Bohr model, it is clearly mentioned that the energy of an electron within the orbit does not change with the time during the course of revolution. Why? Because the electron neither lose energy and nor gains energy. Now, an electron can move from one energy level to another through a quantum or photon jumps only, right? It means when we give some suitable light of suitable frequency, then electron may be jump from one energy level to another energy level, right? When it's reduced in an orbit with the lowest energy, it is said to be in ground state. So when it is present in the lower energy level, it is said to be the ground state. For example, if the electron are present in the K shell or is a one shell, then it is called this is the ground state. Okay, so I hope this is clear to you. Now, next point. This one is also very, very important point. It can jump from its lower energy level to the higher energy level after absorbing energy. It means when you just let me draw the diagram of an atom. Like this is in case of multi-electron atom, right? So let us assume if electron are present in the second shell, right? And now when you give energy, when you give heat, so what happened? This electron jump from this orbit to this orbit, right? From the second orbit to the third orbit. So it can jump from its lower energy level to the higher energy level after absorbing energy. Here at the higher energy level is also said to be excited state. So this is known as excited state, right? So this one known as excited state, right? So this one is known as excited state. So what do you mean by this term excited state, beta? What is this excited state? Excited state means when we give energy to the electron, which is present in the lower energy level, they excited and go to the next energy level, right? And this state is the excited state. And here the time for which electron is staying at this state now is very, very less. It's around 10 raised to the power minus 8 seconds. So this is a very less time during which electron is in present in excited state. As soon as this energy get over, they return back to its ground state, right? So an electron can move only from its ground state to excited state after absorbing energy, or from its excited state to ground state after releasing energy, right? Now, this one, during transition between the two stationary state of the different energy, the frequency of radiation absorbed or emitted is given by, we know that energy delta E. What is delta E? So change in energy is nothing but E2 minus E1. Suppose if the electron present in the first cell and get excited and go to the second cell. So what is the excitation energy beta? That is E2 minus E1. Or we can write Sc is a Sc upon lambda, right? Or we can also calculate C upon lambda is nothing but mu. So this mu is equal to E2 minus E1 divided by this term Planck's constant H. So this is the frequency. Now, this expression is called the Bohr frequency rule. So just remember this. During the transition between the two stationary states of a different energy, the frequency of the radiation absorbed or emitted is given by V, which is equal to E2 minus E1 upon H, where E2 and E1 are the energy and H is the Planck's constant. So this expression is called the Bohr frequency rule. I hope this is clear to you. Now, this is going to be very important. Now we are going to do the calculation part of the and try to remember the formula, so that because many time numericals were come directly based on the formula as well. So if you know the formula, then you can easily correlate the questions, right? So first of all, basically this Bohr model of atom is valid only for the one electron system, like hydrogen having only one electron, like helium plus, like lithium plus 2, like beryllium plus 3. So this this Bohr model of atom is valid only for one electron system, right? One electron system. So just remember this thing, beta. This Bohr model of atom is valid only for the one electron system. Okay, now how we'll calculate the Bohr calculation? What is Bohr calculation is all about? So in this, we have to calculate the radius of the various orbits. So first of all, we are going to calculate the radius of the various orbit. For example, if I'm talking about the radius of the first, it means this this is the nucleus, right? So this is the radius of the first cell. Similar, if the radius of the second cell means this, similar radius of the third cell. So we are going to see how we'll calculate the radius. So just remember the important formula here. We are not going to derive this. Just remember this. Rn is nothing but is equal to n square, h square, 4 pi square, kme square upon z. Don't get disappointed and don't get, this कि हमें ये पूरा फॉर्मूला याद रखना पड़ेगा, ऐसा कुछ भी नहीं है, because we already know the value of h, we know the value of 4, we know the value of pi, we know the value of m, we know the value of e, k, right? So just by putting the values of all the known quantity, what we get like this: r naught is equal to nothing but 5.29 into 10 to the power minus 1 meter, or we say in Armstrong, we can remember like this, right? 0.529 Armstrong, right? So the radius of the nth orbit of an atom, this is the radius of the first orbit, right? So radius of the nth orbit of an atom with the atomic number Z is simply written as like this. So we can remember this in form of Armstrong. So this is the first one. Now we can also remember like Rn is equal to 53 into n square upon Z. So this is in picometer, right? This is in picometer. So this is the formula in picometer. This is in Armstrong, because 5.29 we approximately remember as 53, right? So this true formula we basically use. This both formula are same, just the difference of the unit. So in Armstrong it is equal to 0.529 into n square upon Z, or in picometer it is equal to 53 into n square upon Z. So this is how we can remember this. I hope this is clear to you. How will you derive the expression for the radius of the various orbit using Bohr calculation, right? So this formula you must remember, because numericals were coming directly from such formulas, right? So if you know the formula, then you can easily derive this. From this formula, you can also get to know that is radius is directly proportional to the n. N is a principal quantum number. If the number of shell increases, then radius automatically increases, right? And it is inversely proportional to the Z, where Z is the atomic number. If I'm talking about hydrogen, it having atomic number 1. If I'm talking about helium 2, lithium 3, beryllium, that is 4. So we can write the atomic radius as this. Okay. So I hope this is very much clear to you. Now, this one is also very important. Once we calculate the radius, the next thing we have to calculate is energy. So how will you calculate the energy of the revolving electron, right? So you have to calculate the energy of an revolving electron. So we know that the total energy of the electron is the sum of the kinetic and the potential energy, and it is equal to E is equal to nothing but this. Again, we know the value of 2 pi m e k and h. So just by put the value of this, we can calculate the energy. So this formula you must remember, beta. This one is very important. If anyone asks in terms of erg per atom, erg is a smaller CGS unit of joule, right? So anyone if want this energy in the erg per atom, then you can remember like this. Now this one is important, right? This one is important to learn this, because this one is very important in terms of joule. So what is the formula of energy in terms of joule? So it is very simple to remember. It is nothing but it is equal to minus 21.8 into 10 to the power 19 joule per n square. Or sometime I also remember as E is equal to minus 2.18 into 10 raised to the power minus 18, right? And this is Z square upon N square. This is in joule per atom. आई होप दिस इज क्लियर टू यू। ये मैंने क्यों याद कर रखा है ऐसे, क्योंकि देखो यहाँ पे भी 0.18 है और पावर में भी 0.18 है। तो जस्ट फॉर द सिमिलैरिटी हियर, after the decimal 1.18 is there, and in power also 0.18 is there. So you can remember this as well, right? So I can remember like this, and this is very easy to understand. Minus 2.18 into 10 raised to the power minus 18 as well, right? So this is also you can write. So this two formula in the form of joule per atom. Now if someone, because we know that 1 electron volt is nothing but is equal to 1.602 into 10 raised to the power minus 19 joule. Remember this important fact here. This one is very play a crucial role on solving numerical, because many times you have to interconvert the electron volt into joule or joule into electron volt. So just remember 1 electron volt is nothing but is equal to 1.602 into 10 raised to the power minus 19 joule. So this is the value of 1 electron volt, right? I hope this is clear to you. Good. Now we can actually calculate the value like En, which is En is equal to this. So in terms of electron volt, what is the formula of energy? So this is the formula we are going to use in the terms of electron volt beta, that is minus 13.6 into Z. So in terms of electron volt, we are going to use this formula, like E is equal to nothing but minus 13.6 into Z square upon N square electron volt. Just remember this beta. In case of radius, radius is directly proportional to the principal quantum number, but energy is inversely proportional to the principal quantum number. It means as the number of cell going is increasing, the energy start decreasing, right? So this is the important formula. So I recommend you to just remember this two formula. This two formula is very useful, right? So try to learn this all four formulas, but out of this four, these two are very important. So try to learn these two formula only, if possible, like in terms of joule per atom or in terms of electron volt, right? And remember this small thing, like 1 electron volt is equal to 1.602 into 10 to the power minus 19 joule, and 1 calorie is equal to 4.18 joule, right? So this is how we can actually calculate the energy. Now here important factor is, many of you having question in your mind, why the negative sign is there in the energy? What this negative sign indicate? Whether the energy become negative, how is it possible? Right. So basically, remember here, the negative sign in all the formula of energy does not have any numerical implication, right? This sign only signifies that the energy of the electron in an atom is lower than the energy of the free electron at infinity, right? Or the highest negative value is given for n is equal to 1, corresponding to the most stable orbit. Or in other words, we can also remember like this negative sign indicates that the electrons in the shell are highly attracted by the nucleus, and these are the binding force. This is the force at which by which nucleus bind the electron. So if you want to remove this electron, then you have to give energy so that this negative energy releases, and you get the electron. So this is known as ionization energy as well, right? So you know this thing, this is also known as ionization energy. So here when the n become infinity, when you keep the electron from the far away from the nucleus, right? For example, this is the nucleus, right? N is equal to 1. Here is a first cell. And if you keep this n is equal to infinity, then we know that this is a very large distance. So here the attraction between the nucleus and the outermost electron is almost negligible, and the electron is easily emitted. This is known as ionization enthalpy. It means when the n is equal to infinity, E automatically becomes 0, which corresponding to an ionized atom, that is electron and nucleus are infinitely separated, and there is no force of attraction between the nucleus and the outermost electron. So this negative sign basically represent how this electron and nucleus are attracted to each other. If you want to remove this electron, you have to give energy equal to the negative energy, right? So this is the significance of negative. Now, the third important thing here, that is a Bohr velocity, or we say velocity of electron. So we already calculate the radius, we already calculate the energy. Now in this we are going to calculate, right? Now in this we are going to calculate the Bohr velocity, or we say velocity of an electron. So how will you calculate this, beta? How will you calculate the velocity of electron? So we know that V is nothing but it is equal to 2 pi k Z square, right? This is nothing but equal to 2 pi k Z square upon NH, right? 2 pi k Z NH square upon NH, where we know that we know the value of 2, we know the value of pi, we know the value of k, we know the value of E, we know the value of H. So after putting all this value, we get velocity is equal to 2.18. Just in case of energy, we can also remember now 2.18 into 10 raised to the power minus 18. Here only 2.18 10 raised to the power 8 only, right? Into Z square upon N, and the unit is centimeter per second, right? So this is the formula. Thus, the velocity of an electron in nth orbit of hydrogen atom, we can calculate like 2.187 10 to the power 8 divided by n, because in case of hydrogen, Z is equal to 1, right? So other than hydrogen, you have to use this formula. So better remember this formula only. So this is the formula to calculate the velocity of an electron. Now, what is the interpretation of hydrogen spectrum by the Bohr model, right? So how hydrogen spectrum comes into the picture, and what is the interpretation of hydrogen spectrum by the Bohr model? So let's see this. Now, according to the Bohr model, all through electrons revolve in the stationary energy orbit, but these can undergo transition as shown below, right? So according to the Bohr model, all through we know that the electron revolve in the stationary orbit, but these can undergo transition as shown in the figure. For example, this is the nucleus. This is the first cell. This is the second cell, third cell, fourth cell, fifth cell, and sixth cell. Now, when photon absorb, their energy start increasing, right? So this is the electron and this is the photon emitted. When you give some light of frequency mu, then this electron get excited and goes to the upper energy level. Similarly, photon emitted energy decrease. It means when the photon is absorbed, when we give frequency to the atom, when you give energy to the atom, so it will become absorbed and the obvious its energy become increasing. Similarly, when photon emitted energy decreases, it means when the electrons move from the higher energy level to the lower energy level, it start emitting photons, right? So an electron absorb a photon of light white, it jump from a lower energy orbit and the photon is emitted white while it return to the original lower energy level. It means whenever electron absorb a photon of light, right, while it jump from a lower energy to the higher energy, whenever the electron jump from the lower energy level to the higher energy level, it always absorb a photon. While when the electron moving from the higher energy level to the lower energy level, they always emit a photon. These transitions were proved responsible for the spectrum of an atom. In fact, Bohr explained the spectrum of hydrogen through this transition only. So we are going to see the hydrogen spectrum, which is explained by the Bohr, right? So what the interpretation is? The spectrum obtained consists of a large number of sharp lines, each of which correspond to a particular frequency. These lines are present in UV, maybe in visible, maybe in infrared or electromagnetic spectrum, right? So we are going to study later, that is the hydrogen spectrum. That is, if the any electron fall from any level to the first, that is a ground state, then it is called Balmer series, Lehman series, right? Sorry for Balmer, Lehman series, and it is falls under the UV, ultraviolet radiation. If the electron jump from the any state, any state to the second state, then it is known as Balmer series. And Balmer series, we have a visible region. Now, if the electron falls from the any other state to the third state, then it is known as Paschen series. Fourth, then bracket. Fifth, then Pfund. And if C, then Humphrey series, right? And this is known as IR and far IR region, right? So in the first, that is the Lehman series, we got the UV region. In the second, that is the Balmer series, we got the visible region where we can see all this thing. And from the rest of all this, we having IR region. So just remember this thing, right? So this is basically the spectrum of the hydrogen line. So as we can see that when the electron transit, this is n is equal to 1 and this is n is equal to 2. So you can clearly see there is a large energy difference between n is equal to 1 and n is equal to 2. So this is arranged according to the energy, right? So there is a large energy difference between n is equal to 1 and n is equal to 2. There is a small difference between n 2 and 3. There's also very small between 3 and 4, and between 4 and 5 it's going to be small, and so on. Right. So whenever the electron falls from either fifth state or the second cell or the third cell or the second cell to the first, then it is always known as Lehman series, as we can see here, right? When the electrons fall from any to the second, then it is known as Balmer, then it is Paschen, right? So as the energy changes of the transition become greater, the lines in the spectral appear at the higher frequency, right? As the energy changes of the transition become greater. So as the energy goes on, the lines in the spectrum appears at the higher frequency. So this is how we can actually draw the get the spectrum for the hydrogen. Now, in this we go get the very important formula like Balmer and Rydberg formula, right? So what is this Balmer and Rydberg formula basically is? So in Balmer in 1885 show that if the spectral lines are expressed in the terms of wave number, right, then the visible lines of hydrogen spectrum obey the following formula we can write as, right? So the wave number V bar, we can write it. Wave number is also defined as 1 upon lambda, right? So this is also we can write. So wave number is nothing but 1 upon wavelength. So it is equal to 1.69677, 1 upon 2 ka square minus 1 upon n square. So what do you mean by the why we taken 2 square? 2 square means what is happened beta? Why we take 2 square? 2 square means n value of n is greater than 2. Maybe it will be 3, 4, 5 or 6, and 2 represent the Balmer series, right? So this is the Balmer and the Rydberg formula. Similar for the Lehman series, we can use N1. This is N1 now. This N1 is become 1. For the Paschim series, so on. And it's going to 3 and fit 4, fit 5 and 6. So we can use like this, right? So the Rydberg were above formula, more generalized form, which was applicable to all the series of hydrogen spectrum and can be written as the wave number in centimeter is equal to RH, which is equal to Rydberg constant 1 upon n1 ka square upon 1 upon n2 ka square, where RH is equal to 1.09677 centimeter, right? And n1 and n2 are the integers, where n2 is always greater than 1, right? So that this quantity become less. This is called the Rydberg formula, and RH is called as the Rydberg constant, right? So this is all about the Rydberg formula, and this RH is called the Rydberg constant. So just remember this formula, that is V bar of hydrogen, which is also equal to 1 upon wavelength, is equal to Rydberg constant of hydrogen 1 upon n1 ka square minus 1 upon n2 ka square. Where always remember this thing, where n2 is always greater than n1, right? If n1 is 1, then n2 is maybe 2, 3, 4 or 5. If n1 is 2, then n2 may be 3, 4, 5, anything, right? So this is how we can calculate. Remember also Rydberg constant RH, which is equal to 109,677, and this is centimeter inverse. So this is the unit of Rydberg constant RH. So remember this as well. I hope this is clear to you. Good. Now, where Z is the atomic number of an element, right? So the Balmer series of the line is the only series which appears in the visible region. So this one is very important point. The Balmer series of a line is the only series which appear in the visible region of electromagnetic spectrum. The first, second, and the third line of the spectral series are called alpha, beta, and gamma respectively. For example, H alpha has the wavelength of 4107 Armstrong. Similarly, H beta and H gamma have the wavelength of this respectively, right? So what is this H alpha, H beta, and H gamma? For example, if electron are present and n is equal to 1, this is n is equal to 2, and this is n is equal to 3. So whenever the electron, the first, second, third line of spectral series, right, is called alpha, beta, and gamma. It means when when the electrons come, that is when the electron is in 1 and it's go to position 1, that is known as H alpha. When it is go to the second, then it is known as H beta. Similar, when it go to the third, then it is known as H gamma, right? So we can remember like H beta, H alpha, and gamma. Now, the maximum number of lines that can be emitted for a transition for N2 to N1 when the N2 is greater than N1 is given by this formula, right? That is N2 minus N1 plus 1 into N2 minus N1 divided by 2. So this is the formula for finding the maximum number of lines, right? I hope this is clear to you. How will you find the maximum number of lines that can be emitted for a transition from N2 to N1 whenever the N2 is greater than N1 beta? That is N2 minus N1 plus 1 into N2 minus N1 divided by 2. So this is how we can find. Now, so now we are going to solve some questions so that your concept become very much clear, right? And you can easily solve this question as well. So what the question asks, beta, basically, you have to calculate the energy and frequency of the radiation emitted when electron jump from N3 to N2 in the hydrogen atom. So you have to calculate the energy and frequency of the radiation emitted. So how will you calculate the energy? So first of all, we know energy. When the electron jump from N3 to N2. So let us assume this is N is equal to 1. This is N is equal to 2. And this is N is equal to 3. Now, when the electron jump from N3 to N2, N3 to N2. So sorry, from here only. Let me erase this. Right, N3 to N2. Okay, so the final first position is 1. And this is the final position, right? So we know that delta E is what? That is E2 minus E1. E2 minus E1. Now, what is E2 here, beta? E2 is nothing but this is here in case of E2 minus E3, right? So this is in case the cell number 2 and 3. Yeah, here the emission takes place now, right? Now, how will you write the value of E2? So we know that E2 is nothing but how will you calculate? How will you calculate beta? E2 minus E3. Yes, if you want to calculate in form of Joule, then we can calculate as minus 2.18 into 10 raised to the power minus 18, right? And this is nothing but n square. So n square upon z square upon n square. So what is z here? So z is nothing but hydrogen. So it is 1. So it is z square upon n square. So n square is nothing but in case of I'm talking 2. So 2 to the 4, right? So this is equal to 4. Similar, right? So this is 2 into 2, 4. Similar, if I'm talking about this, so then this also calculated as 2.18 10 raised to the power minus 18 into z square upon 3 3 is 9, right? So this is first E2 minus E3. Okay, now we can take the common. So out of this is become plus, right? So if you take this common, that is 2.18 into 10 k power minus 18 into z square. So if you take this quantity common, then what you'll get, beta? You have left with minus 1 by 4 or minus plus 1 by 9, right? So you just have to solve this only. So this comes out to be 2.18 into 10 raised to the power minus 18. And this quantity comes to 9 for the 36. This is minus 9 and this is 4. So this comes out to be 2.18 into 10 raised to the power minus 18. But 9 charge, it is minus 5 divided by 36. Right? So by this, you can easily calculate this. So this is the energy. So if you calculate, you get the answer. Now, so what you have to do for the calculation of frequency? Because we know that na, energy is nothing, but energy is equal to h mu. So just divide this quantity with h. right? So just divide this quantity with h, which you get this. So this is the formula that the energy we get like this, right? 3.02 into this. Okay, so this is the formula by which we can easily calculate this. Now we are going to see some important numerical more. Before that, we are going to see some more important concept of this chapter, like the dual nature of matter and radiation, right? So what is this dual nature of matter and radiation? So under this, we are going to cover de Broglie equation, right? So we are going to cover the de Broglie equation. What is the de Broglie equation is, and how we can actually use this. So at that time, many of the scientists saying the light having particle nature, someone saying the light having wave nature. So there is a always, little bit confusion whether the light is a particle nature or a wave nature. So de Broglie comes and de Broglie actually tell, okay, if you assume that light having the wave nature, so if you are saying if the wave behave like a particle nature, right? Because if the light having the wave nature, and now you can also say that the light behave like a particle. So if the light which is in wave nature and behave like a particle, what does it mean? It means uh, particle also having wave like nature, right? So the de Broglie found a new type of wave that is called matter wave, and he say that if the particle also have wave characters on it, and particle also behave like a wave, it means every particle have some wave like character which actually give its motion, right? For example, this pen is a particle nature because this having some mass, and now there is a wave associated with this pen as well. When they move from one place to another place, then there's some wave which controlling its motion, right? So their wave is also associated with this. So he discovered the wave associated with the matter wave is called de Broglie matter wave. It means he derived one new wave that is called the matter wave. He also derived an expression for it with the help of Planck's equation and Einstein mass energy relationship. And this expression is given as, how will it derive the relationship better? Because we know that from the E is equal to Einstein energy equivalence, E is equal to mc square. We also know as E is equal to h mu from the Planck's theory, right? So from the Planck's theory, we also know that E is equal to h mu. Now, just equating this two. So on equating this two, what we get? We get mc square is equal to h mu, right? And this is mc square. We can write h mu as h mu is equal to c upon lambda. So just cancel one c with c. The lambda comes out to be mc upon h. Or we say, in case of velocity of medium, we can write mv upon h. And this is h, right? This is h. So this is mv upon. Let me. Here is some correction required. Yeah, fine. So MCC से C cancel हो गया ना, तो क्या बचा? So lambda comes out to be h upon mc, right? H upon mc. Or we say for the medium we use the velocity. C is the velocity of light now. So for medium we use mv. So this is the expression for the de Broglie. We know that mv is also equal to momentum. So lambda comes out to be h upon p. So this is the formula that we derive from this, right? So lambda is equal to h upon mc, or we say h upon p, where p is the momentum. I hope this is clear to you. Right. Now, in case of kinetic energy of the particle is given by the de Broglie wavelength can be calculated by the formula like this. Lambda is equal to h upon under root 2 me. How is come beta? We know that. We know that kinetic energy is what? Kinetic energy is nothing but it is half mv square. Just divide by m and multiply by m. So if we multiply and divide by m, then become uh 2m, and this is kinetic energy, is equal to m square into v square. We know that what is mv? That is momentum. So this is momentum ka square, which is equal to 2m into my kinetic energy. So what is p beta? P is equal to 2 m, and this is kinetic energy. So just put this value. We know that lambda is equal to h upon p. So put this value, so it will become h, and the value of p become under root 2 m and ke. So this is how you got this formula, right? So this formula, that is lambda is equal to h upon under root 2 m ke. This formula we got from this, right? So this is the relationship between lambda and the kinetic energy. So many times the question was asking in which the relation we have to use. What happen when the energy increases? What effect on the wavelength? So we know that from this, that is energy, lambda is inversely proportional to energy, right? So from this equation we can observe this lambda is inversely proportional to energy. Now this equation is also play a very crucial role. This was the second one. This is the third equation, and the first two is this, right? And this one. So the third one is also a very, very important reaction. How is come beta? We know that V is equal to nothing but W upon Q, or we say voltage is nothing but W, or we say in the form of energy, or we say Q is in form of electron, right? So this is E. Now, how will you calculate beta? We calculate now. This is E. So energy is nothing but is equal to V into E. V into E. Voltage into electron. Now put this value. So what you will get? You'll get lambda is equal to H under root 2 M. And instead of E, we put the value of VE. So this is the formula of wavelength in terms of potential, or we say voltage, right? So we derive totally three formula. So we derive total three formula for the de Broglie wavelengths. The one formula is lambda is equal to h upon mc, or we say h upon p. The another formula is lambda is equal to h upon under root 2 me, and the next one is lambda is equal to h upon under root 2 ebm, right? So this is the important formulas that we derive. So just remember this three formulas, and these three formulas is very, very important, and try to solve numerical on the basis of this, right? So this is going to be very important. So just try to learn this. I hope this is clear to you. Anyone, any kind of doubt? Anyone having any kind of doubt, please, you can ask better. No? Okay, chalo. Now, so de Broglie wave are always associated with an electron, and the other microscopic particle means small particles. Thus, for the various subatomic particle, the value of lambda can be given by the following. Now, if I'm talking for the electron, then for electron, it comes out to be 12.27 under root V. Because here we know all the value. We know H, we know 2, we know E, we know M, right? So we know the value of mass of electron, charge of electron, under root 2, and the Planck's constant. So by putting the value, we'll get this. It means for electron, we can directly use this formula lambda is equal to 12.27 under root V, right? Similar for the proton, we can use this formula like 0.268 under root V. For alpha particle, we use this formula 0.101 upon under root V, where V is the accelerating potential of this particle. Now, similar for the neutron, we can use the formula like 0.286 upon this, right? And for the gaseous molecules, we can use like this. That is lambda is equal to h upon m, and this is VRMS. And we know that how to calculate VRMS. So m into VRMS is equal to 3 under root mkrt. So by from this we can also calculate. Now, the number of de Broglie wavelength in a given Bohr orbit is always equal to the orbit number. How? We know that from the de Broglie, that is mvr is equal to nh upon 2 pi. So this is 2 pi r is equal to nh upon mv, and this is equal to n lambda, right? So 2 pi is equal to n lambda. So this one is very important, and try to understand this thing. Now, this question is going to be asked. So try to understand this question and try to solve this question better. I'll give you 2 minutes till I take some water. So just try to solve this question. How will you solve this question? the de Broglie wavelength of an electron in the fourth orbit. So you have to calculate the de Broglie wavelength of an electron in the fourth Bohr orbit, right? Just using this formula only, right? So by this formula only you can be able to calculate this. So you have to calculate the de Broglie wavelength of an electron in the fourth Bohr orbit, right? So just calculate this. Just calculate this thing, beta. I'll give you 2 minutes for this. Okay. So I hope you all calculate this. What is the de Broglie wavelength of electron in the fourth Bohr orbit is? Yes. So let's see the solution, beta. We know that the de Broglie wavelength of an electron is given by lambda is equal to h upon p, or we say h upon mv dash. But for from the Bohr postulate, the quantization of angular momentum of electron mvr is equal to nh upon 2 pi. Now this mv nh upon 2 pi r. Now we know that from the lambda is equal to h upon mv. So just put the value nh upon 2 pi r, which is equal to 2 pi r upon n, where r is the radius of the Bohr orbit in the Bohr model. So just putting the formula n square upon a naught upon z, z is equal to 1 for hydrogen, n is equal to 4 already given. So by putting the value, you'll get 8 pi a naught. So this is the correct answer. So this is the relationship between these two, and by using this relation, we can calculate. Now, let's move to the next question, next topic. Today we are going to cover the entire topic, right? And from in tomorrow class, we are going to do the numerical related to this structure of atom. So in tomorrow class, we are going to solve all the numerical related to this chapter only, right? So let's see. Heisenberg uncertainty principle. So what is this Heisenberg uncertainty principle, beta? And what it states. So Werner Heisenberg of Germany gave the principle of uncertainty, in which he stated that the exact position and exact velocity, or in other words, we can say momentum, right? So exact position and exact velocity, or we say momentum, of the subatomic particle cannot be measured simultaneously. This principle was exactly opposite to the Bohr theory of the fixed position of electron and definite energy of the orbit. This principle can be expressed mathematically as this, like delta P delta X is always greater than or equal to h upon 4 pi. It means when you calculate delta P into delta X, there is always chance of error which is equal to h upon 4 pi or greater than h upon 4 pi. So it is impossible to measure both the position and the momentum of the particle at the same time, right? So this statement was given by the Heisenberg and known as Heisenberg uncertainty principle. Now, what is the interpretation of this formula? What do you mean by this? So above formula can be interpreted as whenever the position and momentum, that is velocity, of a subatomic particle be measured simultaneously, then always a minimum error of h upon 4 pi. Already told you there is always a minimum error of h upon 4 pi magnitude till will occur. By putting the value of delta P in the above expression, we get delta V into delta X is equal to h upon 4 pi. Now, delta V delta X is equal to h upon 4 pi into m. Likewise, just for energy and time, delta E into T is equal to h upon 4 pi, and delta phi for angular motion, we get this. So whenever you try to calculate the what position and the momentum of the particle, right? So whenever you want to calculate the position and momentum of the particle at the same time, there is always a error, right? So there is always a error which may be equal to h upon 4 pi or greater than h upon 4 pi, right? So this is always happening. So I hope this is clear to you. There is no problem in this, right? Good. So this is all about the interpretation of this formula. Now, the above expression also tell us about the following points, like uncertainty in velocity or position varies inversely with mass, right? So uncertainty in velocity or position varies inversely with mass. Thus, it is negligible for the macroscopic object. We cannot draw a trajectory of a microparticle in contrast to a macroparticle. And hence, in light of the Hinsberg principle, the Bohr concept of the orbit of electron become untenable, right? So, uncertainty in velocity or position varies inversely with the mass. So this is negligible for the macroscopic object, right? Because in the macroscopic object, mass is very high. So thus it very negligible for the macroscopic object. We cannot draw the trajectory of a micro particle in the contrast to a macroscopic, and hence, in light of the Hinsberg principle, the Bohr concept of the orbit of electron become untenable. Thus, for an electron within the atom, Thus, for an electron within the atom, the best we can think of in terms of probability of locating electron with a probable velocity in a given region of a space at a given time, right? So remember this, Hinsberg uncertainty principle is applicable only when the location and momentum are along the same axis, right? So this principle, Hinsberg uncertainty principle, is applicable only when the location and the momentum are along the same axis. If delta x is uncertainty in position along the z-axis, then delta p must also be uncertainty in momentum along the z-axis, right? So if both are in same axis. Now, to overcome this, Schrodinger equation comes into the picture. So Schrodinger derived an equation for an electron which describes the wave motion of electron along any of the three Cartesian axes, that is x, y, and z. What the equation is, beta? Just remember this: del square psi upon del x square plus del square psi upon del y square plus del psi square upon del z square plus 8 pi square m upon h square e minus v psi is equal to 0, where the symbol are their usual meaning, like psi represent the wave function, h represent Planck's constant, e represent total energy, and v represent the potential energy of the electron, right? So this is how we can actually derive. Now, the wave function, like this is the wave function, right? So how will you derive this wave function, beta? So the wave function psi may be regarded as the amplitude function expressed in the terms of coordinate x, y, and z. The value of the coordinates is comparison with the wave is given below. Like this psi become positive, this point is known node. So node is a point where the probability of finding electron is 0, like psi is equal to 0. So this is known. For 1s orbital, nodal surface is 2s orbital. So in this, there is for 1s orbital, there is no nodal surface is 2s orbital in a s orbital, like this plus 5, right? So this is called as nodal plane, and these two mutually perpendicular orthogonal to p orbital in the p orbital, right? So these are between the planes. So the electron where finding the probability is 0 is known as node, and the plane where the probability of finding electron is 0 is known as nodal plane, right? So three keywords to be used in the wave mechanical model with their crispy elaboration are given below. So how will you understand this wave mechanical model? So you must know this three word in a better way to understand the wave mechanical model. So what is this three important words, beta? The first one is orbit, right? So what is this orbit? What is this orbit? So basically orbit, it is a two-dimensional imaginary space, right? So it is a two-dimensional imaginary space around the nucleus where the probability of finding electron is maximum, right? So orbit is nothing but it is a two-dimensional imaginary space around the nucleus where probability of finding electron is maximum. An orbit can contain 2 to 32 electrons of variable energy, but of the same family, right? So basically the orbit is nothing but it is a two-dimensional imaginary space around the nucleus where probability of finding electron is maximum. An orbit can contain 2 to 32 electrons of the variable energy, but of same family. On the similar basis, what is orbital? So it is the three-dimensional real space around the nucleus where probability of finding a particular electron is maximum. Now, an orbital can accommodate maximum 2 electrons of exactly equal energy. And what is subcell? Aggregation of a group of orbital of exactly equal energy which combine to form an orbit. These are basically named as we already know, S, P, D, and F. Later we are going to study this thing in a quantum numbers, right? What is subshell? What is the orbital? What is the spin quantum number? These all are going to study. So these three things are very important. That is, one is orbit, and one is orbital, and the subcell. So orbit is a two-dimensional imaginary space, right? And the orbital is the three-dimensional real space around the nucleus where finding of a particular electron is maximum, right? And an orbit can contain 2 to 32 electrons of variable energy, but of the same family, where the orbital maximum have a 2 electrons. Now, what is node beta? So if someone asks, what do you mean by this term node, right? So what is this node? So these are points or a space within the orbital where probability of finding electron is zero. So this is very important. So these are the points or a space within the orbital where the probability of finding electron is zero. Thus we can say that electron density is not maximum at all at the places in an orbital. It may also be zero at the some places. The quantity of these nodes is fixed for a particular orbital and can be calculated in the following manner. So for this orbital, number of node is equal to n minus 1. Similar for the 1s orbital containing no node, right? Because 1 and 1 minus 1 is equal to 0. The 2s orbital, that is 2 minus 1, is contain one node. 3s orbital containing two node. Here we can observe in 1s orbital there is no node. So node is the space within the orbital where the probability of finding electron is zero. So here there is no electron. Now we already studied. There is no electron in this. Electron are present only on this one, right? So there is no electron on this. So this is known as nodal plane, right? This is known as nodal plane. So nodal plane is the node is the place where finding of electron is zero. Spherical as atom spherically disposed about the nucleus. Now, similarly for the p orbital, the number of node is equal to n minus 2, right? N minus 2. In both the above cases, n is equal to principal quantum number. These nodes can be spherical or non-spherical. Spherical node are called radial node, while the non-spherical node are called the angular node. Just remember this. This node may be spherical or non-spherical. The spherical nodes are called the radial node. Spherical node are called radial node, while the non-spherical node are called angular node. For any atoms, radial and angular nodes can be calculated by using the following formula. Number of angular node is always equal to a geometrical quantum number that is equal to n, right? So number of angular node is always equal to L. Similar number of radial node is equal to n minus L minus 1. So what is the total now? N minus L. So just remember these three things. The first one is number of angular node. So angular node. So angular node is equal to L, which is equal to azimuthal quantum number. We know that for S, its value is 0. For P, its value is 1. For D, its value is 2. SPD. For F, its value is 3. So we can calculate this like, right? So if the angular node is 0, it means it is from S subshell. If the angular node is 1, it is from P. So you can calculate angular node is equal to L, right? Good. On the similar basis with a radial node. How will you calculate radial node? So we can calculate radial node like N minus L minus 1. right? So n minus L and this is minus 1. So this is how we can calculate. For example, if someone say for 3p, just calculate radial node. So how will you calculate beta? For here, n is equal to 3, L is equal to what? L is equal to 1 minus 1. So 3 minus 2 is equal to 1. Similar for 2s. If someone say for 2s, you have to calculate. So n here is 2, 0 and minus 1. So 2 minus 1 is equal to 1. So here is only one node, right? So you can calculate radial node. Similar for the 3D, 3, L here is 2 minus 1. So 3 minus 3 is equal to 0, right? Okay. So this is all actually we can calculate this, right? So this is the how we can calculate angular node, radial node, and the total node. So if someone wants to know the total node, then what is total node, beta? Total node. So total node is nothing but it is equal to what? Total node is equal to matlab angular plus radial. So it comes out to be n minus 1, right? This is n minus 1. So total number of node is equal to n minus 1, as you can see here, right? So this is the total node. So this point is very, very important. This slide is very important. First of all, we get to know what is nodes. So these are the point or space within the orbital where probability of finding electron is 0. Thus we can say that electron density is not maximum at all at the places in orbital. It may also have a 0 at the some places, right? So this is the node. Now, on comparing 2s and 2p orbital, we find that the 2s electron spend most of its time close to the nucleus than does the 2p electron. In other words, 2s electron is bounded more tightly to the nucleus than does the 2p electron. And the radial distribution curve for the 2p orbital is given below. So this is the radial distribution curve for the 2p orbital. So the energy of 2s electron is less than the energy of the 2p electrons. All through both the electrons are of the same energy level, or we say orbit. So this is the distance from the nucleus, that is r, and this is the radial electron probability function, which is equal to 4 pi square or psi square. So we get the graph like this, right? So 2 pi is equal to n. 2 pi means where n is equal to 2 and n is equal to 1. So this is 2p. This is 2p, right? 2p means n is equal to 2 and l is equal to 1. So for 2p, we get the graph like this. Now, similar finding are seen in the curve between the orbital wave function and r, with the difference that here negative values of wave function are also visible, because psi can be negative or positive, but psi square can only be positive, right? So for 1s, wait. Huh. So for 1s, so for 1s and 2s, these curve look like this. Like, so this is for 1s, value they start decreasing, and this is for 2s. This value become positive. There is one node now, because we already covered in case of 2s, one node is present. So node is a point where finding of electron is 0. In case of 1s, there is no node is there, right? So this is the form derivation for the 2s and 1s. Now, similar properties are visible in the radial probability distribution curve for 3s, 3p, and 3d. Now, this is for 3s, right? So this is for 3s. So what is the diagram for 3s, beta? How many node in 3s? We already know that node, that is, if I'm talking about the radial node, is equal to n minus l minus 1. So this is 3 minus 0 minus 1. So two nodes must be there. These two nodes are like this. Here is the first node and this is the second node. So this is the radial distribution function of psi square for r versus 3s. So for 3s, we get the structure like this, right? And this is going to be increased, so on. So this is the distance from the nucleus. So this is all about. So this is the first cell, K shell, L cell, M shell. K shell, L cell, and M cell. So this is the first, that is the K shell. This is the L and this is the M shell, right? So and so on. On the similar basis, this is for 3p. This is for 3p. So in 3p, we get only one node here. And in case of 3D, we get zero, no node, right? So the point M in the each curve represents the maximum distance. So this point M represents the maximum distance. What is the maximum distance? That is the maximum distance from the nucleus. So this is a distance from the nucleus. So this is here the distance is 0. Here the distance increases. This is the m. So this represents the maximum distance from the nucleus. Now, for 1s orbital, number of radial node is equal to 0, as we can see that. For 2s orbital, number of radial node is equal to 1, as we can see that. Now for the 3s orbital, we got the 2 node. 3s orbital, we got the 2 node, right? In case of this 2p orbital, we get the 0 node. Thus, the given graph between the psi square and r represent the 2s orbital. So if someone asks which of the following graph represented, so psi square and r represent the 2s orbital graph. So this is all from the quantum mechanical model, and I hope you all understand this thing, right? So before starting quantum number, now we are going to solve some numerical related to these topics only till so far. However topic we covered, let's try to solve questions related to this, and in tomorrow class we are going to discuss quantum number, right? So I hope this is clear to you, right? So let me solve some question related to the previous year examination, what type of question generally they ask, right? So this is the first question, and this question was asked in your advanced paper, right? So this question was asked in your advanced paper. Try to understand this question. This one is very, very important and very easy to understand as well, right? Because this question is basically based on the Bohr model. So we already derived the Bohr model, right? So in this question, they are asking, considering Bohr model of an one electron atom, where the electron move around the nucleus. Now, in the following, list 1 contains some quantities for the nth orbit of the atom, and list 2 contain options showing how they depend on it. Now you have to, which of the following options has the correct combination considering list 1 and list 2. So you have to identify the option, which option is correct, right? So the first one, radius of the nth orbit. So we already derived radius for the radius. We know that Rn is nothing but is equal to 53 into n square upon z in picometer, or Armstrong we have 0.529, right? So n square. So which one is correct for radius of the nth orbit? Radius of the nth orbit is directly proportional to n square. Yani for 1 is equivalent to t. Yani for 1, T is the correct one, right? Now, second, angular momentum of electron in the nth orbit, kinetic energy of the electron in the nth orbit, and the potential energy of the electron in the nth orbit. So you have to derive this. So we know the total energy. So in case of total energy, we know that energy is inversely proportional to what? Energy is equal to minus 13.6 into z square upon n square. So for energy, n minus 2. So here directly, no, it is inversely proportional to n square, right? So it is inversely proportional to the n square. So which of the following is the correct combination, right? So we know that radius is equal to this. So this one is correct. MVR is equal to NH upon 2 pi. So MVR is directly proportional to n. So second, right? Now, kinetic energy Z is the third ka P, and the P that is 4P. So the correct option is first T. That is first option only. Only first one is correct. Rest all are incorrect. I hope this is clear to you. This question is totally based upon the Bohr model of atom that we earlier studied today. सबको समझ आया क्या? Anyone having any kind of doubt, you can ask beta. No? Chalo. Now, let's see the next one. A ball of mass 100 gram is moving with the velocity of 100 meter per second. Find its wavelength. So how will you find the wavelength, beta? How will you find the wavelength of both of the following ball? We know that wave is associated with the particle as well. So which law tells this? Which law is tell about the particle also show the wave-like behavior? Which one? That is de Broglie, right? So the de Broglie wavelength. So we know the formula for the de Broglie. What the formula is? We know that lambda is equal to h upon mv. So here you have to calculate the wavelength. It means lambda. So what is h beta? We know that h is equal to 6.66 minus 34. What is m here? 100 gram. What is v here? 100 meter per second. Right? So just solve this. You can approximately, this is 6 and this is 10 raised to the power 2 to 4. So it comes out to be 6.6, or we say 6.63, both are equal. And 10 raised to the power 34 and 4, that is minus 34 minus 38. Mm, this is 34 now. Okay. Mass, you can take mass in gram. Okay. So this is minus 34 minus, this will be minus 38. Okay. Now, let me check the unit. We know the unit of E is equal to H mu. So what is the unit of H? E upon mu. So we know the unit U is joule. Joule, energy of this is joule, and 1 upon mu. Mu is frequency, second inverse. This is second. So this is a joule second. So the energy of H is joule second. You know the energy of gram, and velocity is meter per second. Meter per second. So the meter per second. Right. So just put the values. We know this 6.6 into 10 to the minus 31. So just put the value. We know in kilogram we convert this. So it becomes 0.1 kilogram. Put the value lambda, we get this 6.6 into 10 raised to the power minus 35. Right. Just converting this into gram, kilogram. Right. This is 100 gram now. So just divide this 100 gram by 1000. So this will convert it into 0.1 kilogram. Okay, so this will become lambda, this will become h, and this will become mv. So h is what? 6.63, 10 raised to the power minus 34. Okay, and m is what? 0.1 into 100. So this is 34, and this will be 1, that is 34, and this is 2. So 36, 35, right? So this comes out to be 6.63, 10 raised to the power minus 35 meter. So which option? That is option number A. So option number A is absolutely correct for this. I hope this is clear to you. I hope this is clear to you. No issue in this. Okay. Now, using the Broglie equation, this is already done. No, this one is the ground state energy of the hydrogen atom is minus 13.6 electron volt. Considering an electronic state of psi of helium plus whose energy, azimuthal pointer number, and the magnetic pointer number are given. It means energy are given minus 3.4, azimuthal number, that is L is given 2, and the magnetic pointer number, that is ML, is given 0. Which of the following statement is that true for the state psi? Now L is equal to 2 represent what? D. It represent D now. Then in which day? 3D, 4D, how many? How will you derive this? Now if the energy is given, then you can easily calculate N. How will you calculate N beta? Because this is for hydrogen atom. So we know the formula, like energy is equal to minus 13.6 into Z square means 1 upon N square. So this value is given, energy is minus 3.4. This is minus 13.6. This is N square. So N square is equal to 13.6 minus minus cancel 3.4. So this comes out to be 4. So N is equal to 2. Right? So N comes out to be 2. 3.6 divided by 3.4. Right? So N comes out to be 2. So it will be It is in 4D state. No. N square, this n square, this comes out to be 4. So n square comes out to be 4. N means 2. There is some, let me check. So 13, this n comes out to be 16. How does it? This is for, wait, considering electronic assay of helium plus. So sorry, there is helium plus is given beta. So we know that for helium, atomic number is 2 ka square, right? So how does it come beta? So it comes out to be minus 3.4, right? And this is the total energy. So let me solve again. Okay. Now we know that energy is what? Energy is nothing but minus 13.6 into z square upon n square, right? Now this energy is given that is equal to 3.4. This is minus 13.6. And we know for helium, Z is equal to 2. So this comes out to be 2 square 4. And this is n square that we have to calculate, right? So this n square comes out to be minus 13.6 divided by minus 3.4 into 4. So this will 4. So this comes out to be 4 for the 16. So n square comes out to be 16. So what is the value of n here? So n is equal to 4. So n is equal to 4 here. Now, if you calculate n is equal to 4, then you know this will become 4D. And for 4D, how many angular node we have? So 4D, two angular node? No, 4D. So the angular node is equal to L. So L is equal to 4D. It is equal to 2. So it has a 2 angular node. Yes, this is true. 0, 1, 2. Right. It is a 3 radial node. Let me check. N minus L minus 1. So here N is 4. L is 2 minus 1. So 4 में से 3 गया. This is 1. So this is wrong. The nuclear charge experienced by the electron in this state is less than the 2e electron, where electron is the magnitude of electronic charge. It is a 4D state. This two statement is correct, right? So A and C. So both A and C, these two statements are absolutely correct, right? So this is the way how we can actually solve this question. So this is the formula for solving this question, and this is how the actually it comes out to be, right? So it is a 4D state and it has a two angular node. Now, let's see the next question. An electron in the hydrogen atom undergo transition from an orbit with a quantum number ni to another with a quantum number ns. Right? It means initial to final, where Vi and Vf are the respective initial and final potential energy of the electron. If Vi by Vf is 6.25, then the smallest possible Nf is. So how will you calculate beta? We know that potential energy is equal to kZe square upon y, or y, or we say radius, right? So we know that this is equal to k Z E square upon R, right? So radius of the Bohr atom or monoatomic element, we already know this thing. We already know this thing. Radius is also equal to 0.529 into n square upon Z, right? So this is Ui upon Uf. So you can write now Ui upon Uf is equal to R2 upon R1, right? Because we have a relation like this. Now, what is this R2 upon R1? Because we know that R2 upon R1 is also equal to in terms of N2 ka square upon N1 ka square, because we know this relation. Okay. And this is already given. N2 upon N1 square is already given. So we can write like N2 upon N1 is equal to under root of 6.25, because N2 square upon N1 square is given, right? So this comes to under root of 6.25. So which is equal to N2 upon N1 is equal to 2.5, right? So what is N2 upon N1 better? 2.5, or we say N2 upon N1 is equal to 5 by 2, or we say N2 is equal to 5 and N1 is equal to 2. So this is how we can solve this. I hope this is clear to you, right? Good. Clear है सबको? ठीक है. So this is the way how we can actually calculate these values, right? So if you have any problem related to this question, beta, you can ask me. No? All clear? Good. So this question I am giving you as a homework question. So try to solve this question, right? So this is your homework question. I'm starting tomorrow class from this question as well, from this question itself. So till try to solve this question. What the question state in the question? A hydrogen atom in its ground state is irradiated by the light of wavelength 970 angstrom. Now taking Sc upon E is equal to this EVM, and the ground state energy of the hydrogen atom is 13.6 electron volt. The number of line present in the emission spectrum is. So you have to calculate the number of line, right? So in the hydrogen atom, its ground state is irradiated by the light of wavelength 970 angstrom, taking Sc upon E is equal to 1.27 10 to the power minus 6 electron volt, and the ground state energy of hydrogen atom is this. So you have to calculate the number of line present in the emission spectrum, right? So you just need to calculate this number of line. So today we are almost covering all the important topic of this chapter. We are covering like Bohr model, we also cover the various calculation related to Bohr model. Like in Bohr model, we found the formula for energy, radius, and velocity. After this, we also looked at spectrum, hydrogen spectrum series. So we already discussed about this, how the hydrogen spectrum series comes, how is the interpretation of this, in which the visible region falls, in which the IR region falls, in which the layman region belong to UV rays and all, right? So we are discussing about the hydrogen spectrum. And after this, we are also discussing about the de Broglie, and in de Broglie wavelength, we saw different formulas, right? So we saw different formulas related to this. Next, after this, we also look on what about the Heisenberg uncertainty principle, right? So in Heisenberg uncertainty principle, we also observe about this thing, how to calculate the position and momentum, and it is impossible to measure both the position and momentum of the particle at the same time. So these type of thing we already covered, right? And the later on, we are already solved some numerical which is related to these topics. Okay. So we already covered three, four, five. This is the fifth numerical, which I am giving you as a homework. So far we four questions we already covered, right? So for tomorrow class, for tomorrow class, so what we are going to study now in next class, we are going to study the quantum number, right? Because only quantum number and electronic configuration, small things are left behind. So we are going to study the quantum number, the small things, and going to solve more numerical. So for tomorrow, we just try to finish all the theory in the 40 or 30 minutes. And after the next 1 hour, we are going to solve only numerical, right? So numerical related to this. So I hope you understand all the things, and you have any doubt related to this, you can ask in the next class, right? So this is all for today. Let's meet on the next class and try to understand the more topic, right?